Over here, we have a network with junctions and some values of the flow through each junction. Using this information, we can find the amount flowing through x1, x2, x3, x4, and x5 through a process called network analysis. If you're already familiar with this concept, you may pause this video and give finding these values a shot, otherwise you may keep watching to view my solution.
Before getting into the video, you should know that this is actually a segment of a larger video series called the Ultimate Linear Algebra Guide, where I go into these concepts more in depth and have problems and solutions attached to every single video. The guide itself is free, however the videos do take a bit longer to make since they're a lot longer than these videos, so go ahead and check the description to see if I've released the corresponding Ultimate Linear Algebra Guide video for this one yet, and if I have, go over there. Otherwise, you're welcome to keep watching this video until I do eventually release the guide. Also, make sure you subscribe to my channel so you'll be notified when I release the Ultimate Linear Algebra Guide video for this concept. Okay, let's get back into the video.
Before moving on to the more complex network, let's start off with this more simple network over here with one junction. So the most important equation that you must remember whenever dealing with any junction in any network is that flow in has to equal the flow out. This is the most crucial equation when we are dealing with network analysis. So here, the flow into the junction has to equal the flow out of the junction. So 25, which is a flow into this junction, has to equal x1 plus x2 because those are the flows out of the junction. So in a larger network, we have to apply this equation to each and every junction within our network. So let's go ahead and do that for this network over here. Starting with junction 1. We want to apply the equation flow in is equal to flow out for this junction. Here we have 20 flowing in and x1 and x2 flowing out. So flow in is equal to flow out, which means that x1 plus x2 is equal to 20. I prefer to write my variables on the left-hand side because that makes solving the system and creating a matrix a lot easier, but this is equivalent to the equation flow in is equal to flow out. Now let's apply that for junction 2. So here we have x4 flowing in and x3 and 20 flowing out. So x4 is equal to, the flow in is equal to x3 plus 20 because that's the flow out. I always recommend that you write the equation with flow in and flow out on different sides before you rearrange to solve for the constant. So we always want to rearrange the equation to solve for a constant, but before doing that, in order to avoid error, I highly advise you to write flow in and flow out on different sides of the equation. So now let's rearrange and solve for the constant. Once we rearrange and solve for the constant, we get that minus x3 plus x4 is equal to 20. I recommend that you write your variables in ascending order, so x3 will come before x4 in order to avoid any confusion when you're making your matrix. Now let's move on to junction 3. So we have two flows into junction 3, x2 and x3, and two flows out of junction 3, which are 10 and 10. So flow in, which is x2 plus x3, has to equal flow out, which is 10 plus 10, which is equal to 20. Now we'll have two more equations because we need to write one equation for each junction, and there are 5 junctions, which means there must be 5 equations in the system. So the fourth junction, which will create our fourth equation, will be flow in, which is x1 plus 10 is equal to flow out, which is x5. So x1 plus 10 is equal to flow out, which is x5. Once again, we always have to rearrange to solve for a constant, so we want to move all of the variables over to the left-hand side preferably, and the constant over to the right-hand side. So let's do that. Once we rearrange and move the 10 over to the right-hand side and the x5 over to the left-hand side, we'll get that x1 minus x5 is equal to minus 10. Once again, I just rearranged to solve for the constant, so we moved all the variables to the left-hand side and the constant to the right-hand side. So now that's the fourth equation. Let's move on to create the fifth and last equation. So it looks like we have a flow in of x5 and 10 and a flow out of x4. So flow in has to equal flow out. So x5 plus 10 has to equal x4, since x4 is the only flow out of this junction. So now, once again, we rearrange to solve for the constant, which gets us that minus x4 plus x5, because we want the variables in ascending order to avoid any confusion. Minus x4 plus x5 is equal to minus 10, solving for the constant. So now, these are our 5 equations. This is the first equation, this is the second equation, this is the third equation, this is the fourth equation, and this is the fifth equation. So using these equations, we have a system of equations that we can solve for x1, x2, x3, x4, and x5. Taking these equations and putting them into a matrix gets us the following matrix. Here, the first column of our matrix represents x1, the second column of our matrix represents x2, third column x3, fourth column x4, and finally the last column, or the last column of our coefficient matrix, x5, with the column that we're added on representing the constants, because this is the augmented matrix. If any of this seems new to you and you haven't really dealt with solving systems like this, I recommend that you check the card that should appear in the top right corner of your screen to see my video on solving systems of equations like this, where I go more in depth into the process. However, at this point of the course, I kind of assume that you're already comfortable with the idea of Gaussian and Gauss-Jordan elimination to convert a matrix to a reduced echelon form. So I am going to use a calculator to do so, but if you're not, I highly recommend that you watch my video on how to solve systems of equations so you actually know what I'm doing here. Okay, so once we take this matrix and convert it to a reduced echelon form in order to solve for our variables, we get the following matrix. Here, as you can see, we went ahead and converted our matrix to row reduced echelon form where we can solve for each variable. Here, as you can probably see that every single column doesn't have a leading one. So let's identify the columns that don't have a leading one so we can see which variables we have to make a free variable. Also, since every single column doesn't have a leading one and we don't have an impossible equation, that means that this system has infinite solutions. So here we would have x1. It looks like x1 has a leading one over here. We have x2. x2 does have a leading one. x3, which does have a leading one. x4, which has a leading one. But x5 doesn't look like it has a leading one. So that means that x5 is going to be our free variable. If you need help in identifying a free variable or identifying that this system has infinite solutions, I've linked a video that you should see once again in the top right corner of your screen, which goes over how you may identify how many solutions a system has and how you can identify free variables. So go ahead and watch that video if this doesn't make sense to you. Okay. So now that we've identified our free variables, we can go ahead and solve the system. So since x5 is our free variable, we can go ahead and set it equal to t, where t is some real number. So x5 is equal to our free variable t, where t is some real number, and using this we can solve for the rest of our equations. So x1 would equal, well, we'll have x1 minus t, so we can solve for x1, which will become minus 10 plus t. All of our solutions are going to be in terms of our free variable because we have a free variable in our system and it has infinite solutions. x2 is going to equal, well, once again, we have plus t. So this time we're going to have minus t on our right-hand side, so we'll have 30 minus t. x3 is equal to, well, we have a minus t on our left-hand side, so when we move it to the right, it'll become a positive t. So looks like x3 and x1 are the same, which is minus 10 plus t. x4 is equal to, well, if we move the minus t to the right-hand side, we'll get 10 plus t. And as I said above, x5 is just equal to t because that's our free variable. So here we have a solution to this network. Now, the reason that we have a t here is because an infinite value of solutions could satisfy this network and have those respective flows through each junction. So as long as we keep the value of t consistent, which is we set x5 equal to one specific real number, we will be able to satisfy the system. So this is the solution to the system, and it's perfectly fine that we have infinite solutions, just means that there's an infinite number of ways that we could satisfy this network over here.
So that's the end of the video. If you have any questions or spot any errors, you're welcome to leave them in the comments, and I'll respond as quickly as possible. On screen, you should see a link to my last video alongside a playlist that contains every single individual linear algebra guide video that I made so far. And I hope to see you in the next video. Until then, goodbye.